चेला the madam है ना 30 seconds is 30 seconds. really चेला the madam है ना 30 seconds is 30 seconds.
Good morning. Today we have two lectures by Professor Ravindra Pandey, and he will discuss about the future challenges of nanotechnology in the specific area. Before the commencement of the course, before the commencement of the today's lecture, we want to announce that after this session, we will circulate a Google form in the chat box where you will be asking to take a small quiz, and then you will submit those that will be helpful for us to grade evaluate your performance for this course. So the link will be shared at once after the lecture is open. You will also have to fill the Google feedback form that will be shared on your email accounts, and please be sure to submit it before 5 p.m. today. Please, I welcome Dr. Pandey sir to share his lecture. Thank you.
So Namaskar, it's day 5, and let me apologize for being a Saturday morning and still you are going to do some physics. But thanks to the Jabalpur sort of host, Professor Lambert, Durgesh, Nandini, and Bhavna to accommodate my traveling schedule to keep this on Saturday morning. And so I hope to sort of give you one of the examples of what we can do with the design. And then I think one of the questions was asked yesterday about nanofibers, so I'll try to address it. And then from there, the last lecture is going to be summary, future, and where we are, and open to discussions. So, like I said, we'll discuss about composites and see how can we design or understand uh, the properties of material in a device configuration by calculating the current voltage characteristics. And then we move to sort of a novel materials feature and summary of our workshop. So let me see who has asked the question yesterday. Dr. Sumaya, are you there? Or Natarajan, I don't remember. Dr. Natarajan, did you ask the question about fibers? Okay, so what I do is, he's not there. So let me skip this part and then I'll come back in the second half of the talk. So that if he's around, then I can answer his questions. So so we'll look into the electron transport in nanomaterials, which are going to be used for solar cells. And the key thing is we have to differentiate between a solar cell, photovoltaics materials, or photocatalyst materials, and then the materials we use in battery. So in photovoltaics or photocatalyst, the transport is governed by electrons, which is important. How fast the electrons move to respective anode or cathode and electron holes. But in battery, we do not worry about the electrons. Basically, this is dominated by the movement of ions going from anode to cathode. They are two sort of characteristics, different ones for battery and solar cell materials. So I'll just give you a little glimpse because we already talked about a DFT. So just a couple of slides is how do we do these electron transport calculation. And we look into some of the examples, which we should be aware of it because we are really talking about ultra thin samples and how does the transport occur in these ultra thin samples. So as we know is for solar cells, we have been using so-called NP junction devices where sort of photon comes in, hits the material, formation of electron-hole pair, electron goes one end and hole goes the other end. So the question we're going to ask, if you would like to use graphene-based materials, so what kind of thickness is a sort of appropriate for these devices in solar cells? Because it depends on the application. If you really want to use as a transistor in electronic devices, then definitely a monolayer is a little more appropriate. But if you're looking at the solar cells, the key thing is the absorption of the photons. So as I showed you for conventional silicon-based solar cells, they had to have a little higher thickness so that they can absorb light efficiently. So we look into these two cases, and then we talk about can single layer boron nitride be a good dielectric material, because we had to have a good insulating substrate which sort of blocks the leakage of the carriers from the device. So this is a sort of a device. Typically, is that we have the channel material. It's what we would like to have in sort of two-dimensional material, but it's connected by left and right by the contacts. And in this case, we assume the contacts are gold 111 surface, and they tend to be a semi-infinite. That's the key thing. So we have a quantum region for the channel material, but for contact is going to be semi-infinite. And you can see at the interface, these are the yellow ones or the gold one, looking at the graphene. So they, in a sense, either on top of the carbon atom or somewhere in the ring side, the hollow side. And same is true with the boron nitride. So the key thing is whenever we make these contacts, we want to make sure there is a very minimum strain at the interface. Because if we have the strain, that lattice mismatch, then it's going to introduce a lot of other effects which is going to degrade the performance of a device. So that mismatch is also becomes important in making the contacts with the 2D materials. And then we had to also be careful about the bias voltage. And because we are looking at applying this bias over a nanometer thickness. So this 1 volt per nanometer is a pretty high field. And what we find both experimentalists and in our simulation, that the breakdown of the material occurs around the voltage of a field of 2 volts per nanometer. And here's the type, which should be 0.1 eV per nanometer. So this is a cartoon which we do. So like I said earlier, this is in between is our channel material, 2D material. So we call it the scattering region or the quantum region. And it's surrounded by these contacts, layers of gold, which is semi-infinite. So this is a sort of a quantum cluster or quantum region embedded in semi-classical region. So you have these sort of mismatch about the physics of the system, quantum versus semi-classical. So the trick of the trade is what we call is a Green's function. And a lot of mathematicians, they know about the Green function. I will not go in details, but one easily calculate the current going through the system if you go left to right, given by the gamma of left lead, gamma of right lead, and then you have Fermi-Dirac distribution function. So if you remember your solid physics, or that whenever we apply the electric field, the Fermi level shifts up and down. And what we have is application of the field is in this direction, the left goes up and right comes down, or vice versa if you go this way. So this is again is a small cartoon to explain what happens when you apply the electric field, and then how does a current flow. So if this is our device, we have the quantum material, 2D material, and as you know, the energy levels are quantized. We have a semi-infinite contact left and semi-infinite contact right. And they are, again, is a semi-classical approach. So they have a more or less a continuous energy distribution. And we do a volt is equal to 0. So you can see there's a mismatch between the top of the left or right contact with the channel eigenstates or channel energy level. So once we apply the field, the levels are going to shift. And I said earlier, left is going to go up and right is going to go down. And when at certain bias, when the left one sort of comes in nearby at the same level as our quantum or 2D energy level, then we can see the current starts flowing. So this is start. Now we're going to apply the field. We applied the field, and you can see there is a slight movement, but still current is 0 because it's still there is no sort of this left level has not come up to the level of our 2D material. So if at all electron wants to hop, it needs some kind of energy barrier, which is overcome the energy barrier which sort of is not sufficient at this value of the voltage. So we further up the voltage, and you can see now this is almost near. So it is much easier for electron to hop from left lead to our 2D material. And current is beginning to rise, and you can see once it matches, and then current flows, and then sort of you collect to the right contact. So this is sort of a principle of electron transport, and we use Green's function to describe the left and right contact, and the channel, of course, is going to be our DFT theory. So let's pick up our example in fullerenes, which is a 0D material, and our idea is can we manipulate the fullerene electronic structure by doping? Because as you recall, fluorine has a wide energy gap, about a few electron volts. So it's not going to be sort of easy to use fullerene as electronic material for our either diode or transistor devices. So if I use semiconductor analogy, we have a group 4, which is a fullerene, and if I go to group 3, is going to be again P-type, N-type. If you go to group 5, it's going to be P-type dopant. So we consider both boron and nitrogen sort of coming or interacting with the C60. Now you can have two choices. Either our dopant atoms can come and sit inside the cage, or they can simply substitute one of the carbon atoms. So we considered the both possibilities. It's either interstitial site or the substitution site. So if you look at the boron, in this case is boron simply adds to the C60 and sits in the center of the cage. And the other option is we look into the boron, which simply substitutes one of the carbon and sits on the surface of this fullerene cage. So we have BC60 or BC59 or NC60 or NC59. So they are sort of like two different cases. So we go through we optimize DFT calculation, the geometry, look at the structural properties from their band structure, density of state, and then further we do the Green function calculations. So from there we have a current versus voltage characteristics. And this is exactly similar to what experimentalists measure from any materials, device materials. They have IV characteristics. They can say what kind of current is going to flow through this device. So we sort of simulate exactly similar characteristics for experimentalists. So we look into it. If you look at this, the black curve, this is C60, is pristine, and you can see it's rather flat. This is in a microamp, and at certain voltages there's hardly any current because of the gap, and then afterwards it takes over. And if you calculate the conductance, which is again is the inverse of your current, is about 1 volt, is about 0.06 G naught. Our resistivity comes over 220 kilo ohms. If we insert boron in the cage, nothing happens. Because we expect the same thing is boron is sitting in the cage and simply not modifying the electronic structure of fullerene enough so that we can have a current which is different from the pristine case. But interestingly, if you see, if boron substitute a carbon, such a significant rise of current. And this is what we call is N-type doping, because boron goes to carbon side. It has a 3 electron, carbon has a 4. So substituting carbon is going to have 1 extra electron available for conduction. And simply after about 0.6 eV, this takes over and provides a very, very large current. If you go other way around, the nitrogen, so carbon has a 4 electron, nitrogen in a sense 5 electrons, goes at the carbon side, it really wants to have 1 electron. So it is at a P-type doping, and what you can see here, nothing changes. Either this is C60 nitrogen sitting in between, or nitrogen substituting the one of the carbon atoms in C60. So what happens is this comes out is the C60 definitely allows the boron modifying its characteristics to give us a very, very large current, but nitrogen doesn't do anything at all. So you can see from here is we can do a lot of simulation considering a lot of dopant impurities. And then we tell the experimentalist these are the dopants which are likely to give you a higher current or modifying the electronic structure than the rest of the other elements or other dopants. So simulation is working for experimentalists to provide a guidance so they can pick or choose which one to use as a dopant. Now let's move to graphene, monolayer and bilayer and trilayer. And if you recall yesterday, I want to summarize our results when we considered the trilayer case. Either boron nitride is sandwiched between graphene, or graphene is sandwiched between boron nitride monolayers. And for these cases, doing optimization, structural property, and electronic property, band structure and DOS, we found is the first case, the graphene takes over, and the gap is hardly zero, is hardly any gap at all. But for the case of when graphene is sandwiched in boron nitride for both ends, which you expect because it provides the dissimilar electronic configuration or structure or polarization to these carbon atoms in the carbon lattice, gap opens up pretty high, about 57 MeV. And as you tell the experiment, they say, well, that's fine, but can you do some transport characteristic so we can see how does this gap sort of reflects in an IV characteristics. So we do the same thing, take the DFT density, feed into this green function approach, and calculate IV currents. And if you look at this graph, you wonder, which I did when my student showed me this graph, that something is wrong. Because both cases, the graphene is in between or boron nitride is sandwiched, the current is more or less same. And you see here, the gap is different. So something is not making sense. So I told my students, go back and do more calculations, have a tighter convergence parameters, but he came back with the same graph. So we thought is if this is correct, let's try to understand what is going on. So what we have is called transmission function. And so you can see exactly the states available for transmission or transport of electrons. So what you expect is no bias if you don't apply any electric field. The black one is the first case, where boron nitride is sandwiched in graphene. And for this case, we have zero gap, hardly any gap. And you can see indeed, there are a finite dense transmission function or density of the states, if we may call, around Fermi surface. It makes sense. But if you look at the other case, where we have a larger gap, what you find is, yes, it's true, there's a gap here. But if you apply the electric field, what happens is, because of the shifting of these states, the both cases have a finite transmission function near Fermi. And this is why what we have is metal-like conduction for both cases. So what it comes out is results are correct. Although the trilayers, they have a different energy gap, but they show more or less same metal-like conduction in the low field region. And even if you have a zero field gap or the finite gap, it does not suppress the current. So next question you ask is, results are correct, and they do not, in a sense, reflect what we have from the band structure calculation. So what is difference here? Difference is, in this case, we are using the device configuration. So our material, the tri-layers are connected to the gold left and right, which acts as a contact for the device. So the question comes down to is, let's see what kind of role this interface is playing between gold, carbon, or gold with boron for these two tri-layer cases. So you go down, and what we call is plot the charge density. And this really figure tells you, indeed, the interface takes over the intrinsic property of the material. Because if I pick up a case, graphene, boron nitride graphene, okay, and these are the contacts, left, gold, corner. And if you see here, there is a significant overlap of the electron density. Means gold is really forming a strong contact with carbon. If you go to the other end, where my graphene is sandwiched between boron nitride monolayer, you can see this covalent bond of boron and nitrogen. Nicely, this is a graphene. But here you also see the extent of overlap is more or less same or higher than what we have between gold and carbon. So gold and boron forms really very, very strong bond. And this is in a sense true because boron is electron hungry. And gold, as we know, is a metal. There's a lot of electron floating around. So whenever they come to near each other, they form a very strong bond. So you can see that for the given device configuration, the both tri-layers are going to behave the same because there is a strong bond at the interface. And this simply takes over. So our guidance is to experimentalists, whenever you make a device, you have to really, of course, think about the materials, but also you have to worry about what kind of bonding we have at the interface. And that's a sort of a trial and error in looking at the weaker interface bonding versus stronger interface bonding. But if this is true for tri-layer, which is really is thicker than a monolayer, then what is going to happen for monolayer? Let's see. So what we do again, we pick up now a monolayer graphene and boron nitride. So you can see here, this is the density of states. And now we are playing the game is we consider a strong interface bonding case where distance between gold and our carbon or boron is small. And we also consider called weaker bonding, where they are separated far apart, and see if it does matter in terms of the current voltage characteristics. So if you look at this case, both for graphene monolayer or boron nitride monolayer, this is again is coming out is semiconducting, and you have a finite density of states at 3.1. As you move further, you can see at 4 is this finite sort of density of states becomes a really Dirac cone like graphene. And this sort of gap also becomes pretty large here. So indeed, the distance between contact and our 2D material does play a role in inducing a density of states. Is a strong case or weaker case. So if you look at from density of states to called transmission function, and same thing we do here is This is a contact. This is our 2D material. We simply play with the distance between these two. So for the case of graphene, you can see here, this is 3.1, which is our equilibrium separation. There's a large, dense, finite transmission. Now we are separating again from 3.1 to 3.4, it reduces. And at 4, which is a weaker bonding with the contact, it simply becomes small, but still we have these channel states. And this makes sense because graphene is a zero gap material. If you look at the boron nitride, remember boron nitride is semiconducting, it has a gap. And like we found here earlier, when the contact boron nitride molar distance is strong or small, still we have the finite density of states, a transmission function. But as you increase the distance, it goes down, and at the weaker bonding case, you can see it mimics the semiconducting behavior. So this again is a computer experiment, shows you that even at the monolayer level, this interface dominates, and if he weakens the interface effect, then the material's intrinsic property reflects in the IV curve. And you can see here the coupling wise also, it shows is indeed there is a sort of an interface charge density in either graphene case or boron nitride case, which sort of plays a role in doing it. So so far so good. By varying the contact, you can play the game of strengthening or weakening the interface effects. But when I talked to my friend in doing experiments, he said, Ravi, that's not possible, because you take the substrate of contact, simply you deposit your 2D material. It's not easy to manipulate the distance between the two. So we thought, okay, now instead of changing or varying the distance, let's increase the thickness of the 2D material and see if it does it matter. So what you're looking here is a graphene. We have monolayer, bilayer, and trilayer. So in a sense, by increasing the thickness, you are weakening the effect of interface. And that again shows up here, that for a monolayer, again, there's a very, very large sort of a transmission function. You go to bilayer case, which is in red, it reduces. And for the trilayer, it also goes down, but it remains finite, which is fine, because graphene should have a transmission function at near Fermi because it is zero gap material. Switch to now boron nitride, and you can see here monolayer definitely is going to transmit electrons. Bilayer little less, and trilayer case, it mimics the intrinsic property of material, which is semiconducting. So the message comes out, at the monolayer level, all the graphene is a semi-metal or zero gap material, and boron nitride is a semiconductor. They have similar transmittance or IV characteristics. But as we increase the thickness, the boron nitride again shows it's being a semiconducting, and graphene shows being a zero gap material. So question again is, or rather guidance to experiment is the monolayer devices, the interface is the dominating effect. So you have to be careful about choosing your sample thickness before you make these materials for solar cell devices. And then again, it comes down to it is a monolayer boron nitride may not act as a dielectric material. You have to go to a multi-layer or thicker boron nitride sample to use as a dielectric material. So we published this paper came out, and then, as you know, is people of course going to read it, and then comes back with their experimental results. And it's just a beautiful thing, you can see, like I said, boron nitride has a gap. But what we found in a monolayer case is like a graphene, ohmic-like conduction. And this is an experimentalist colleague, he did the experiment for monolayer boron nitride. And you can see here, this is slight, is a plateau, but more or less is ohmic-like conduction. But when he goes a thicker sample from monolayer to 7-layer, and you can see, wow, it's just like a diode, the semiconducting material. So you can see is the interplay, which we found earlier also, that the thicker the boron nitride sample is going to mimic the material's property. And it really comes out nicely in experiments. So it really feels good that at least something is nicely sort of going on between our work and I call the real world. Now let's move to a little more complex problem, and that's going to be, any question? No. Now is experiment is giving us the data to see if we can simulate the experimental device configuration. And so one of my colleague, Dr. Yap, he said we had to make this kind of a transistor device. So you had to have a sort of a source and drain along the plane, but you got to have also the gate arm. So he's looking into boron nitride nanotube on graphene. And you can see here it's nicely grown. This is a graphene flake, and this comes out to BNNT tube. This is again is a little more SEM graph, magnifying, as this is a junction, this is a boron nitride nanotube, and this is a graphene flake. So he looked into it, and then of course he wants to make sure that he has a really BNNT sitting on top of graphene. He does a Raman, and you can see the Raman peaks are coming out from graphene as well as boron nitride. So this is definitely is the device configuration BNNT over graphene. So he said, Ravi, can you model it? And I said, okay, let's try out and see what exactly is happening at the interface. So this is our model, a simple model. You can see that the graphene, and this is a BNNT. So to make it simple, you have to play what you call simplify the model rather. So what we have done here is simply taken the graphene and placed boron nitride on top of it. In reality, if you look into it, really is boron nitride is going penetrating the graphene lattice. So this is not exactly the model what we have, but our idea is to let's start with a simple picture and see what does it tell us. So first thing you look into it is what is happening at the interface. What kind of bonding is going to happen? Is there any polarization? So this is a pristine graphene sheet. You can see the nice electronic cloud coming at the benzene ring. This is the hexagon. And that shows is the pi electron cloud. It's very, very flexible. And if you bring in the boron nitride nanotube on top of it, you can see is a polarization on the graphene. So indeed, the contact was made in experiment. It is influencing the property of a graphene by polarizing the carbon atoms electron density next to the boron or nitrogen atoms. And you go further and look carefully. Is graphene is accepting electrons from boron nitride or vice versa. And you can see nicely that N atoms, we project out this called the different planes on the BNNT, indeed is acting as electron donor. Because this is, I call is the excess electronic density, if you look at the scale here. And as you move out, the density is more or less small. So indeed, we have the localized charge density in the vicinity of nitrogen atoms sitting on graphene. And then from there, you calculate the density of states, the transmission function, and the IV characteristics. And this is a very nice result in a sense. Although it's a very simplified model, but it tells the current versus voltage. This is our zero. This is a positive bias. This is a negative bias. So graphene in red behaves like a graphene. Zero gap material is very, very high current as you apply either positive or negative bias. But if you bring in this BNNT, what happens at the interface? We see some sort of a plateau here, which reflects the intrinsic property of BNNT. Because BNNT is a semiconducting. And then, of course, current rises because of the presence of graphene. So you can see here is by, again, playing around and making all these novel devices to basically alter or modify the behavior of graphene. And if you take the pristine graphene, you can see here it does not have a diode-like behavior. And diode-like behavior, as you can see, is at the near zero, is a flat, and then current takes over as you start increasing the voltage. But if we add the BNNT on top of it, this sort of material can definitely be used as a device material because it does have a diode-like behavior by having a very, very small or negligible current around zero bias. So that's again is what I describe, that the BNNT presents, we can have the switchable transport properties, and by graphene being there, definitely we have this the very, very high electron mobility, what they call ballistic nature of mobility. We retain it, but we sort of include this switchable or diode-like behavior in the system. And this is again is sort of my colleague then did some experiment, and he does find that this heterojunction device does have a sort of a diode-like behavior, which can be used for the field effect transistors. So I hope I have given you sort of a glimpse of the materials. How can you calculate the materials properties? Then how can you image them using scanning tunneling microscope? This we covered the three topics yesterday. And today we took the material put in a device configuration with the context, and found out is at the monolayer level, it doesn't matter what the material is. The interface takes over. But if you increase the thickness of the material, then basically we recover the properties of the material, which is then reflected in IV characteristics. And finally, we also saw that how can you modify the graphene by placing the BNNT on top of it. So we can retain the mobility part, which is a strength of graphene, but at the junction with the BNNT, we again recover or we induce the diode-like behavior. So this is the end of this part. And any questions here before I go to the nanocomposites? About the question was asked yesterday. Questions about transport? No? So, Dr. Somesh, I remember you asked about nanofibers. Is that correct? Okay, good. So you're here now, so I can go in the beginning of the talk and just give you what kind of calculations we can do to look into the nanocomposites. So we are not doing exactly the nanofibers, but we are looking at the CNT or graphene embedded in a polymer matrix and see how does it influence the mechanical response. So a few years ago, we got a project from NASA, and what they call is they want to develop sort of nano composites, which definitely is going to be carbon nanotube based, and with a definitely provides this again is I call the buzzword is ultra high strength, lightweight structural material for down the road for deep space exploration. So this is again is a big project combining both experiment and theory, led by Professor Odegaard at Michigan Tech. So for those, just to give you what exactly the polymer composite materials is. So we have the composite basically is a matrix. Let me go. This is our matrix, and this is called as a reinforcement, the secondary. It could be fiber or it could be something different phase and so on. And the key thing which we are from simulation focusing on at the interface about this fiber and our polymer matrix. So what is coming out is I think is known that these fibers or the different phases or even a nanotube material, what they do is they sort of increase the strength of the matrix, because at the interface, if you have the mechanical stress, they can easily be transmitted to fiber or a nanostructure across the interface. And then condition is this, of course, is going to be strongly bonded if you need to have a called stiffness by strength in the composite materials. Any question? No. So that's a little, again, is a cartoon, which we have the graphite. Then, of course, you do surface modification by, again, is organic molecules. And then you have this resin, the matrix polymer, epoxy resin in this case. And then we do the exfoliation and all other intercalation and other processes. And then we have is called nanocomposite. So like we have the band structure or the solar efficiency or other plots in mechanical engineering world, they have called HB plot. So what you're looking at, they are is in a sense the Young's modulus versus tensile strength, just to see how well the material, where does it sort of fit in terms of the stiffness and strength. So you can see here is if you look at the foams only, hardly any sort of stiffness in terms of the Young's modulus, and strength is also very little. As you move up, we have the graphene polymer composites. Further down, we have the fibers, and now we have the carbon nanotubes. So you can see here is pretty high tensile strength, as well as we have the large Young's modulus. And thus we would like to be there. Advantage is now is strength is pretty high, but the material is still ultra light, which can be used. And the good thing here is the manufacturing technology or platform is already there. Now the companies are making these fiber composites, and you can see here is again, this is a composite here, and this is sort of zoom in. You have the fiber which is dispersed in the polymer. Now, if you look at the interface, so this looks like a really mesh. But if he comes from atomistic point of view, the physics and chemistry, that what kind of bond does this fiber or a nanostructure has with polymer? If you remember, polymer is always a carbon-based organic molecules. So they are going to have a sort of a carbon interaction called sigma bond, and then we have this pi polarization, pi electronic clouds perpendicular to the surface. So if you bring in our nanostructure is going to have pi-pi interaction, but sometimes they also have some kind of electrostatic interaction which is weaker. This is again a weaker van der Waals interaction. And then some of the polymers, ligands, they also form a chemical bond. So all sort of things sort of occurs at the interface when we have a fiber reinforced composites. Now, how do you do the simulation? So always remember is if I pick up this picture and try to model it, it's going to be a complex and a tedious and a long process. And as you know, the experimentalists, they don't want to wait for another couple of years to understand what is going on. So my approach, or rather our group's approach, is always try to sort of simplify the process which you would like to simulate to have, I call, a zeroth order approximation, just to understand, and in a simple picture, what are the factors which are governing the interaction. So instead of taking the solution or a large number of polymers, we pick up a simple monomer. And looking at the carbon nanotube, we assume is because these carbon nanotubes have very, very large diameter. So what they have is sort of a flattened surface. So instead of picking up the nanotube as it is, we say let's take a cross section of the surface and simulate as a graphene. So this is more sort of a tractable model, which results can be out in few weeks. And then once you apply the periodic boundary condition, you can have this is our graphene sheet, a cross section of this surface of this carbon nanotube, and these are the special DGEVA. One time I knew the acronym, what exactly is, but I forgot. But we had to rely on a chemist. But if you do Google, you can find out. Is one of the polymers is called epoxy resins. It's commonly used in this research area. So what you do is, again, you take the surface and you look at the where does my polymer molecule, monomer, sort of sits in on the surface. So you, again, constrain and you say, let me go only perpendicular surface, keep graphene as a frozen, like a rigid, because carbon-carbon bond is strong, but let molecule relax. So molecule is sort of relaxed, coming down to the surface and rearranges itself depending on the interaction from the surface. So doing all these calculations and then analysis, what we find is for this particular class of monomer, the interaction is governed by van der Waals interaction. Is weak. Now, of course, we have the oxygen atoms in the monomer. We have a small degree of interaction called covalent polar interaction. So this is one of the class of monomers, but we do another monomer called epoxy resin, BMPM. And whenever you have resin, they have called hardener. And they have different classes. Hardener is a DTDA and DABPA. So all these corrections find is for the resin, we have the mixture of the higher contribution comes from van der Waals, small from covalent-polar interaction due to oxygens, but the hardener is they are nothing but aromatic rings. So we have only the van der Waals type. So what? So when I talk to experimentalists, say that's fine, but how does this, the understanding of the nature of the bonding reflect in the mechanical response? So let me see if I have a slide or not. No, I have no. So what we do in experiment, they have called pull-out test. So to calculate the mechanical response, they have the composite and simply they take apart. And from there, they fit into some of the equations and get the response in terms of gigapascal. Strain also comes in. And of course, this is the binding energy. So you can see here, the blue part is reflecting, is called stiffness. And the red part is the stress. So this is this sort of a cartoon telling us where does either resin or the hardeners, they sort of fit in this graph. And you can see definitely is they are more or less same here. The epoxy and the BMBM and DGBA more or less same, but there's a difference in hardener. DABPA or DTA are distinctly different from resins, which makes sense, but that's the case. So now is what we are trying to tell experimentalists is if you look at the DTDA, is the interaction is purely van der Waals interaction. There is no covalent polar contribution to the interaction. And that's why you're going to have a higher mechanical response compared to the other cases. So now is they are working on such monomers or such resin or hardeners which does not have or which have a minimum sort of number of these polarizable oxygen or nitrogen atoms so that they can sort of yield a better response for the composites. And that's why it's coming back to again, the interface does matter. Either you look into the electronic properties or mechanical properties. So let me stop here. And I hope I answered your question, Dr. Somesh, that DFT does can provide the information about how strong your fiber in a given matrix is, but is an indirect way. Is that okay? Oh, can you unmute him? Dr. Somesh.
Hello, sir. Yes, sir.
Yeah,
hello.
Go ahead.
Sir, okay, sir. Yeah, it is very good, sir. But
can you speak a little louder?
Sir? Hello, sir. Is it my voice?
Can you speak a little louder?
Hello.
Yeah, go ahead. Boliye.
Sir, I am a new beginner of DFT density function theory. But how do I use DFT in my experimental results actually? Because I have some optimized values and experimental results in my work actually. How do I use, that means how to simulate these results using DFT theory?
So for Dr. Somesh, your system is very, very complex. So
okay.
Like I said, is the code which I can think of is doing a large number of atoms is called siesta. And then you have to get hold of a person who can do a little modeling or find a student. And first thing is, what are the system you have? See if you can make a very, very simplified description of physics and chemistry involved in your system. And from take that model and simply once you have the energy versus volume or energy versus distance curves, so we can mimic your pull out test. And we just published, I think I don't have a reference here, let me see. You can get the reference from there. This came out in ACS. It's here, I don't know if you can see, the ACS applied polymer materials. So it sort of gives you the details of the model. And if you have a further questions, send me an email.
Yes, sir. Yes, sir.
And we can talk more about it. See if it.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Okay.
Thank you, sir.
So this gives you an idea. Is really we have very simplified picture.
Yes, sir. Yes, sir.
If you want
I can
to
understand
move,
it, sir. But I have some doubts. Yes, sir.
Can you open something? If I can hear, I cannot hear.
Thank you very much, sir. Thank you, sir.
Oh, okay. The other thing, Dr. Somesh, is if you look into it, I can again give you some idea about not doing DFT, but doing called atomistic molecular dynamic simulations.
Yes, sir. Yes, sir. Yes, sir. Thank you very much.
Where you can deal with thousands of atoms.
Yes, sir. Yes, sir. Yes.
And really simulate.
Definitely, sir. Definitely.
Yeah. So I'll connect you to one of my students. She's doing those MD calculations, and can help you out if you need to set up the model. Okay.
Yes, sir. Yes, sir. Definitely, sir.
Yeah. So just send me an email. I'll take some time, but definitely I'll respond to you.
Yes, sir. Yes, sir.
Any other questions on Saturday morning?
Thank you, sir. Thank you, sir.
Sure. Thanks, Dr. Somesh. I think most of the participants are here. That's impressive. No questions, so let's take a break. And when we start, what is time now? 11:32, in about 15 minutes? What is time? No, but when do we start the next one? 11:45. So let's meet in about 13 minutes. Okay? Yeah, good. So see you in about 13 minutes. Thank you. Okay, so let's start the last lecture. Where is it? Yeah. Screen is coming up. So let me go full mode. Get my pointer. So yesterday, I was thinking about late last night is exactly we are talking about these materials and energy applications, but question aaya ki exactly how much does it cost currently? So I will share that typically, again, this is coming from Google, so you have to think about is the estimated one, and that a average family has about 3 kilowatt solar system requirement. And as we know, most of us have AC, so it's gone up to about 10 kilowatt. And but this number really surprised me, that if you want to install 1 kilowatt system, is about 1 lakh per kilowatt. So what I could see here is in a 10 kilowatt supply is going to be expensive, which I see is beyond our sort of academic families to do it. But hopefully not in my generation, but in coming generation, this cost should come down. Depends on the new materials and new shape and engineering designs. So in this part is going to be easy. Simply is not my work. Basically, I have taken from the other works and other review articles. Looking at just giving you an idea about is both ways, either taking the existing material or technology and simply changing the design aspect, or you bringing in the new materials for doing it. And if I have time, I think I'll spend just a few slides about a new material which we have simulated, a palladium chloride, dichloride, to look into the solar cells. So that was the theme of our workshop, and I hope last 4.5 days, I call rambling, continuous, trying to sort of give you glimpses what can be done. This is our aim, is to have a new material device which is connected to, again, material because of NP junction requirement for solar energy. This is for a photocatalyst materials. And these are the choices what we have. It's metal, non-metal, and organic. And since we are talking about the nanoscale materials, the advantage we have is we can exploit the quantum confinement effects by tailoring either the band gap or a surface selectivity. And then we have also the large number of atoms available at the surface for reaction to occur. But there's these are the pros, if I call it. There's a con also, is since we are talking about nanoscale, one has to be very, very careful about the interface if you're dealing with these electronic devices. So I hope I showed you definitely we can do design by doping or making sort of a new materials, shape or defects or nanostructures, is a part of thing I covered it. But I'll do just a quick one, the recent work about the heterojunctions simulation, and give you some glimpse what is out there in Word from experimental point of view. So this is the work is we're looking at is like earlier we looked into the monolayer, different kind of monolayers, and then we looked into high pressure phase transition. But here the key thing is the word is called phase engineering. So we looked around and we found there is a PdSe2 monolayer. That's in a pentagonal form. You can see here forming the pentagons. And this is a puckered. So this PdSe2 in pentagonal structure is a layered material. So simply like a Scotch tape method, you can exfoliate from bulk crystals. And it has a nice gap, about 1.3 V, which is the maximum for solar absorption. This is softer than other monolayers, MOS2 or PdS2, and mobility is also is pretty high. So coming from graphene point of view, as we know, the boronite graphene, they have called hexagonal structure. So idea is we sort of move from pentagonal to hexagonal structure, what kind of properties this material is going to have, and can we use this one to make heterojunctions, which I'll come a little later. Now, there's a route is you can go from high pressure phase transition from pentagonal to hexagonal phase, but then it's going to be a metastable. And for applications, we need stability at the ambient conditions. So we looked around and say, there is a way by what they call is a lithiation or delithiation process. So what you do is basically you absorb these lithium atoms on the monolayer, and expectation is this adsorbed configuration is going to accommodate these lithium atoms and going to expand out from pentagon to hexagon. And once you have it, then you take the lithium out. And expectation is this hexagonal structure is going to be stable. So this is it's called a distortive phase transformation by doing lithiation or delithiation process. Now the question you may ask is why lithium? And as you know, this is going to be size dependent. So it's much easier, and lithium being is a 1s2 2s1 electron. So is a 1s electron is available. So it's easier to get absorbed, but it is smaller in size. So it's going to distort the pentagonal structure slightly. And then you can sort of take it out. So you make this transformation from pentagon to hexagon by adding or removing lithium atoms. So this is a sort of a cartoon, like we talked about. You start with the ground state, penta, then you add lithium atoms. And again, one has to be a little judicious about choosing how much lithium you want to add. Because the reason is once we add it, we have to take it out also. So we have to find an optimum weight percentage. In this case is about 8%. You add it. Now you can see here is lattice is going to distort, and then what you do is take out the lithium atoms. So you retain this called TPDSE2, which is hexagons, a hexagonal structure. And this is a barrier process because we are adding and removing. So you can see here, if I take the energy versus the lithium atom and we plot it, you can see the energy is sort of becomes a minimum and then rises. So this 8% sort of kicks in nicely and expanding the lattice or making a phase transition. And this is a process you can see. That's our pentagonal structure. 1, 2, 3, 4, 5 PD and Se atoms. Now we're starting adding the lithium. So now is sort of it opens up, further opens up, and then it becomes a sort of a steered case, step case structure, which is indeed is a hexagonal if you look at from the top. Then what you do is typical band structure calculation and see what exactly it is, and we find is indeed as a gap, but the gap tends to be an indirect gap, because if we look at the gamma point, the direct gap is much higher than the indirect one. So it's about 0.8 EV. So if you recall,
the solar absorption is the maximum at 1.3 eV. But here gap is only 0.8 eV. So the T phase or hexagonal PDS2 definitely, if you use directly in photovoltaic as a photovoltaic material, is going to be very, very poor, because it's not going to get absorb solar radiation effectively as the material with 1.3 gap. But advantage we have is it has a very, very high mobility. So the concept came in is, why don't we use a heterostructure solar cells? So what you do is you pick up your PDSE2 and then form a heterostructure by picking up another transitional metal compound, is MOS2. And then you have is called a type 2 structure, and I think I have a slide. Yeah. So this is a multi-junction we call is, you can see, this is a conventional one. We are N-type, P-type, and this is a depletion zone. But if I add the material called type 2 now, heterostructure, where we have the high band gap, which is MOS2, and then we have a low band gap, which is a PDSE2, our material. You can say recombination layer, and then you have transparent electrode and back electrode. So you can see the advantage here. For this case, when the photon comes in, simply it takes care of the material's band gap, whatever it may be. But here, because of high band gap and low band gap, what we are capturing, you can see the radiation, the peak is about 500 nanometers, but also we are capturing, because of being a low band gap, a large part of so-called the red region. So the absorbance of the solar radiation becomes a little higher than what you expect in single material. So and then we have, again, it depends on the location of the conduction band of our MOS2 or PDS2. One can see it can act as a donor or acceptor for the material. So you have got the PDSE2. So what you do, you take the PDSE2 and then start adding the heterostructure. Instead of MOS2, the series of transition metal monolayers, the sulfides and so on, which are known. So you can see the heterostructure is with MOS-Se2, MOTE2, tungsten selenide, tungsten sulfide, and telluride. So these are some of the cases. And we looked into S2-Se2 combination. And then you calculate this called power conversion efficiency. This is called band offset. And the band offset comes from the location of the bands in our MOS2 layer and PDSE2 layer, because we are forming a heterojunction. So the first thing criteria, which is well known, is you have to have this offset. It's a small value. And once you have it, you can have a very nice power conversion efficiency. So for all these cases, you can see the PDSE2, MOSE2, the pentagonal structure, or the tetragonal, hexagonal PDSE2 with MOSE2, but with 3 layers. Has a pretty good power efficiency, about 15 to 20%. So from there, you can again plot, this is sort of a table or a graph looking at the band gap structures. Then from there, you get the offset, and then you calculate the power conversion efficiency. And like I said earlier, this turns out to be pretty high, about 20% in some of the cases. In other cases are very, very small. So you can see again is the advantage of this simulation approach, that once we know what the material is, and then simply we make the heterojunction and predict the power conversion efficiency. So for an experimentalist, it is easier to simply pick up this case with MOSE2 or down here with the MOS2, which he can see these two heterojunctions have a potential for a higher efficiency compared to the other heterostructures. This again is an equation for conversion efficiency, which again comes from the band gap, the offset, and the area and the mass which we need to do it. So this is again is a sort of a cartoon. It's taken from, I think, one of the papers in 2019, which tells you the manufacturing process. That substrates, they are commonly used. Epitaxial methods for 2D materials is going to be the CVD-like approach or epitaxial approach. And then what you need to basically worry about what exactly the lattice match is between the material which we grow and the substrate. And from there, we have so-called the post-growth processing to use these materials for solar cells. It's called wafer bonding or anti-reflection coating, or how to sort of place these solar cells on a grid. This is again is a very, we call spaghetti noodles graph. Is numbers are all over the place, but it tells you simply a sort of an idea about the progress we have made in almost last 40-45 years. So this is the region is we have back in 80s. We're talking about the efficiency, the cell efficiency, not the power efficiency. The cell efficiency about 20%. And now you look at here, we are talking about well above 40%. And if I look at the so-called the emerging cases, or let's look at the multi-junctions cases, heterojunctions in purple, you can see they are the highest one. Is about now 40, 45, 46, 47% number is here. And then if you look at the emerging ones with the nanomaterial in orange, where is the orange? Orange is here. You can see still about 25, 26% is coming out. But remember, these numbers are the lab numbers. The robust technology which is out there is still the silicon one, which is, you can see in blue. It's coming in about 20-25%, which we have in the market is a silicon-based technology. So this is all about the novel materials and make a junction. We can use also the like a graphene on semiconductor junction to take advantage of the graphene, which is a high electronic conductivity. And remember, graphene is a zero gap material. So the photon comes in, it doesn't get absorbed. There's no gap. So graphene in a sense acts as a transparent material for solar radiation. And of course, it has a flexible. The other thing is called tandem junctions. So this is again is similar to what I described, multi-junctions, where you have stacks of these NP junctions of semiconducting materials with a different band gap energy. And then finally also comes out, and again in lab scale, or dye-sensitized organic solar cells, which I'll give you a little glimpse of. Simple the question. Okay. This is again a cartoon. I think I showed you in the first day that graphene is used as not as a solar cell material, but as a sort of a transparent material to provide the interface so that our electrons can really move fast towards the cathode. And like I said earlier, is a zero gap material, so it really absorbs hardly anything. 2.3% is nothing. So this is the way silicon is the material for electron and hole, but then electron moves up, sees graphene, and boom, they move to the cathode or the anode. I said tandem junction again is a multi-junctions, and this is our conventional. We have NP junction, but now you have sort of a combination of tungsten disulfide, WS2, and a silicon. And then you use a graphene as an electron collecting a transmitting layer to take advantage of the mobility. You can have instead of two, you can have again is NP, NP, and then NP, NP, and then P prime, N prime, depending on what you want to do. So you're taking advantage of the solar spectrum, even part of the UV, if you have a higher energy gap, or part of the red, if you have low energy gap. In a single material, we only capture around yellow, green yellow sort of region efficiently, which is 1.3 eV band gap. That's then again gives you an example. If I pick up a silicon only, you can see the current coming out is in red. But once we add this high band gap material, you can see is a larger current comes out from the solar cell. And that's because of the high band gap, low band gap heterojunctions. Then we have similarly is the new materials coming out and called perovskite materials. And then reason is being they have a band gap of 1.7 eV. Silicon has about 1.1 eV. And then if you look at the efficiency is about 40% and above. And if you look at the individual cell where we have only the perovskite, the efficiency is only about 25%. So look at the advantage almost doubled once we have the high band, low band gap materials in a cell. So this is in a sense is the advantage because now we are looking at the available materials what we have. And simply you start making these tandem junctions to increase the efficiency of the cell. This another information is coming out is you have to collect the photons. So what you do is, as we know, photon gets absorbed, but only if it sort of hits the electron. Then you have this sort of movement and the electricity current sort of takes in. But if you have the shape, when you're talking about the pyramid shape, so basically what you're doing, you're increasing the time of photon to travel further, which subsequently increases the probability with the collision before light sort of a photon goes away from the lattice. So this improves again the efficiency, but again is as we know, every bit counts. So this is helpful, but this is simple a designing aspect of solar cells. So this is I think I showed you earlier in the big plot, and this is zoom in. Like we talked about silicon, it's about 25%. And as we got these tandem cells, heterostructures, we really shoot for about 40% efficiency. That's a big improvement. That's again coming out in the lab scale is it's called dye sensitized solar cells, and this is really at the molecular level because you're really taking advantage of the dye molecule. So what you have is these are the contacts, the left and right, and you have the molecule. The photon kicks in, but at the same time what you do is, because you have to have the electrons, source of electrons. So you have it's called a donor molecule, a donor ligand. So it provides these electrons, photon kicks in, scatters, and then in order to attract this electron, basically you have the acceptors, and goes to TiO2, which is again well-known conducting oxide, and then connects to the contact. So as you can see, we are dealing only with the organic molecule. So obviously the cost is going to be very, very low. So we don't have to have fancy either CVD or MB equipment or even patterning based to be used for silicon-based solar cells. Then some work is going on. Now I switched to from solar cells to battery. And as you know, the battery, we have the anode and cathode, but we also have the electrolyte, which sort of facilitates the migration of these lithium ions. So this is a slide I showed you yesterday, that the lithium sulfide, if you go from Li to sulfur, we have this presence of polysulfides, which forms and ultimately they degrade the performance. So idea is, can we reduce the migration of these polysulfides, which definitely provides the capacity loss or impedance rise in Li anode. So people are working actually to make a new generation of these electrolytes, which reduces the migration of these polysulfides. So that's again is an incremental step to improve and durability of these lithium-based batteries. Then I don't know if you remember the slide, is the work is going on in lithium oxygen batteries, which is theoretically is expected to have very, very high efficiency. People are again using so-called lithium, sodium, and potassium. And the concept is the same. Here you can see that's our anode, that's our cathode. But instead of a sulfur, we are using the lithium oxide-based compounds. Then again, is one has to design anode, electrolytes, cathode. And you can see at this end, we are using from DFT to MD to phase field methods called multi-scale approach to look into this design aspect of these materials. And of course, the challenge experiment is we still do not have any working prototype for metal oxide battery. So just a comment. From battery point of view, is it is promising, lithium sulfur, but is really a very early stage in development, and we had to address a lot of challenges before it comes in the market. We talked about it, the design aspect, and we have to worry about in different interfaces, phases here. I think it's a double here, the design and then understanding about the electrolyte and electrolyte forming the sulfide polysulfide solution. And then you need to definitely have experimental characterization, which is really expensive techniques to understand what is going on within the battery before one can improve the performance. That's again a cartoon, is like we discussed. There are different venues, and this is a good topic actually. Is if you're looking for something to contribute towards the battery research, you can see the field is wide open. Okay, you can look into the dimension reduction, where we had the quantum confinement effects kicks in. Composite formation. Of course, you can play around with the doping. In this case, either nitrogen or carbon in graphene. You can go polymer, quantum dot, metal, anything you can play around, which is very easier to do experimentally. Then you have, of course, you control the morphology, the particle size or thickness of the film, or the surface, grains on the surface, how crystalline the surface is. You can look into the effect of encapsulation. How does it affect the properties? Or of course, then how to modify or change or bring new electrolytes within a battery. So I think the last few slides, just to give an idea, is what has happened back when I was a student and now, and it's almost 30 years. So the topic is to do the defect in oxygen vacancies in MGO. We wrote a program. It took about 5 years, and there's a long line of codes. It's a photron called IceCap. And when I did the calculation, so we are looking at this hyperfine constant, means is this electron trapped in oxygen vacancy, how does it interact with the magnesium nuclei? So this is a EPR measurable sort of a constant, which we can also calculate it. So when I saw my result, I got this correct sign, but the magnitude was really wrong, several orders of magnitude higher. But my advisor said, your PhD is done. Now, same thing in 30 years, you can calculate the same thing, and within 10 minutes on your laptop with 1% of accuracy. So really, in computationally, we have come a long way in providing a cheaper and powerful resources. And this is because of, as we know, is a clock speed. And you can see, is back in the 90s when I was doing it, it's about 10 power 7, 10 power 8 hertz. And now look at the number here is almost 3 orders of magnitude higher. So is a faster calculation can be done. And the price is really has come down tremendously. Back in 90s, we had about transfer price we are talking about. You look at it is in dollars, it's very small fraction, but now it is further down, is we call in pennies and rupees, which is amazing. And as we know, is a single CPU nowadays can definitely have billions of these small pieces. So this is all about CPU, but I think the current generation also looking into call GPUs. Is a graphical interface, and it again is the advantage what you're talking about. It takes the complex problems into the separate task, and this is really in terms of the parallel computing is a blessing in disguise. It really provides a much faster response time, or the calculation can be done in days rather than in months. That's a big plus for us. So ultimately, what going down in terms of moving this silicon-based technology to the nanomaterials-based technology in terms of either solar cells or the batteries is a bottleneck. What we call it's really we need to have a very expensive equipments to understand that the fundamental both physical and chemical processes. And of course, it's because of the lack of these equipments or resources, we have very limited understanding. And then finally, once even you understand and you have the lab, the question comes down always from the lab to production. The scaling up is the biggest hurdle for these materials to be used in market. But to me, is a little worrisome thing is about the safety. And as we know, the devices are getting smaller and smaller. And the question is what happens when it gets broken and when you inhale these small nanoparticles of cobalt or nickel, which you have in your cell phone doing it. And it is known, especially the carbon nanotubes, definitely they could go inside your lungs and simply sit there and provide the inflammation or infection in doing it. So one has to be really worried about all those things as well. And then we all know is once silicon cell phone or mobile phone dies, what happens to the battery? And that's really, we are contributing towards called toxic waste and nano pollution. So we have to be very, very careful for the future generation, how we use these materials. And finally is the people who like the diamonds is they are going to be worthless. So this one has to worry about the generation down the road. And oil, as we know, is we're relying less and less once we have the good solar energy component kicking in into our electricity distribution. So this is the end of the workshop. And as we know, we have to acknowledge, especially myself, my gurus, because of their help, I'm here where I am. First and foremost is Sharma from Sagar University and John Whale from Manitoba, who have really provided me sound training and guidance over the years. Then, of course, you have to acknowledge contributions from your students, both undergrad, grad, postdocs, and a lot of colleagues over the years. I've been working almost in academics for 25 years, so I developed a very nice collaborations, both in India and abroad. So that's really helpful in doing it. But again, we had to really thank the local organizers, Dr. Bhavna Singh, Durgesh, Nandini, and Mamta, Lambert, because without them, this course definitely is going to be not possible. They wrote the initial proposals and got the approval from MHRD. And lastly, I had to thank, but before I think last thing is just to let you know, all the PDF files will be available, and Dr. Bhavna Singh is going to send you shared drive or zip folder in doing it. Yeah. And this is again, if you do Ravi Pandey at Michigan, I pop in, but this is my email address. And please feel free to contact me. I do reply to every email, but sometimes it takes time. But I'll definitely respond to you. Just let me just write that you attended the GIAN course. It gives me a little background about your questions and my answers. But I do have to thank you guys also. Listen patiently even on Saturday morning, my rambling, and without them is definitely will not be offering this course. But I really want to send the message, which is over these I found a difference between East and West. When we give lectures, come here in India, is nobody asks any questions. If you go to West, and every student is asking questions, no matter how the question is, we call this stupid or naive, but they ask it. So I like this slok actually. This is already in our Shastra. Yata khanan khanitren naro varadi gacchati tha guru gatam vidyam shushru radhi gacchati. We really want to dig deeper. We had to have queries, especially if you want to learn from a teacher. So please, my little message to you, or request to you actually, next time whenever you go and attend talk or something, don't hesitate in asking questions. It's good for both ends. It's for you, yourself, and also for the teacher. Because sometimes teacher, they don't know the answer. So they can go back and then look into it. So the queries is the must if you really want to move up, and in the ladder, especially in terms of the knowledge. So thanks again, and namaskar. Thank you, Dr. Naidu. That's again a message from my teachers. They always encourage me. I asked, "Is aapko kya guru dakshina de?" And they said, "Well, you should be approachable." And that's what you do as a teacher.
The forum is open. If you have any question, please write in chat box.
So messages again is queries, queries, queries. And some, unfortunately, or fortunately, I don't know how to say, in our system, it does not our thing. Restorative phase transformation. Nice question, Ayushi. So as we know, is phase transition occurs either you apply pressure or you heat the system.
both temperature based or pressure based. But here the question is, can we use the so-called the adsorption process without using the expensive either high pressure or high temperature thing? So I take but it works only for a few cases. We have to be very judicious in choosing. So in our case, we have the pentagonal structure, which, as you know, is little dense or tighter. And as we know, is the graphene is hexagonal. So idea came in, can we make a transition from pentagonal to hexagonal without using either high pressure or high temperature methods? So this is well known in the literature that you have these lithium atoms because they are small in size, but they are still reactive because they have a 1s electron. So they can easily form a bond. So in a pentagonal structure, you bring in these lithium atoms, but not all of them, only few percentage. And in our case, it's only got 8%. So they go inside the lattice, and by forming the bond, they expand it. Once they expand it, you take the lithium atom out. And then what the lattice remains is going to be your hexagonal. Now the question is it going to be stable? Which we had done the calculation and found out, yes, indeed it is stable. So this is called a disruptive or phase engineering in the world. But as you know, is because you have to have a compact structure, which you would like to do for a little more flexible structure. It works only that way. So it's a limited applicability. Now let me see. The other question is, that's a good question. So Yogesh, have you made graphene?
Yes, sir.
So the answer is making a high quality pure graphene is next to impossible.
Yes, sir.
Is very, very expensive. So an oxygen, you know, is available. So what people have done is they use called reduced graphene or reduced graphene oxide. So oxygen is involved in the lattice, but not completely. So advantage what you have is again is a material which is a high mobility, but also because the oxygen, it has the gap. Graphene is zero gap material. So low cost manufacturing, as my personal opinion, going to come from graphene oxide, not from graphene. But it still is debatable. So in your lab, you can easily make graphene oxide rather than graphene. And that's why people have started using it.
Thank you, sir. There is another question from Professor Nelsa. We are modeling perovskite solar cell using SCAPS 1D software. Is it possible to model DSSC using any software?
Yes. So who was the question? Dr. Abraham. So this SCAPS 1D software is what we call is a software which takes the parameters from experiment and gives you an idea about the efficiency. Okay. What I have shown you, you don't need any experimental input. You start from first principles. You build your model, you optimize the structure found the ground state, and then from there you calculate the band structure, electronic properties, and then the cell efficiency. So DSSC is very easy to simulate because it has only organic molecules from first principles. But I don't know about any software which can use. I bet SCAPS should have some kind of a way of simulating DSSC the way you would like to do it.
Is there any question? I request all the participants please turn on their video so that we can take a group photo. Kindly please open your video so that we can take a group photograph.
Done. Done. Okay, all the best. Take care.
Thank you very much.
Dr. Naidu.
Thank you, sir. Thank you very much, sir, for today's interesting session. All participants are requested to please solve the final quiz to obtain their participation certificate. The quiz will be open by 2 p.m. today. Please ensure to submit by 5 p.m. The link will be made available in the chat box as well as your Google mail account. It is my great pleasure for being a course coordinator of 5 days GIAN course on nanomaterials by design for energy applications. Today is the final day of our program and I will be glad to highlight our learning journey till date. Foremost, special thanks to Professor Ravindra Pandey sir from MTU, USA, as he said yes to our proposal for being the foreign expert in MHRD sponsored course. We will also very grateful to his hard work and dedications of preparing and organizing the study material. Furthermore, let us see the brief of our discussion, which started on 22nd Feb. From introduction and synthesis of nanomaterials, followed by various characterization techniques. We discussed about the Raman spectroscopy, luminescence, atomic force microscope methods, quantum behavior material at nanoscale. The next talk was based on photovoltaic solar cell, hydrogen storage devices, simulation techniques for nanomaterials, and graphene-based devices. We also looked at block theorem, block function, Hartree approximation method, and density function theory. And finally today, we discussed about nanocomposite devices and novel materials. Hope it has been a great opportunity to learn and grow for all. We would be delighted to hear your feedback. So please turn on your video and share your words. Participant, you are now requested to share your feedback with us so that if any improvement required, we can do it.
Namaskar, madam. Thank you. Here, Dr. Vijay Inge here. Hello.
Just a minute, sir. Professor M.V. Somesh, please be continuous, sir.
Good afternoon, madam. Good afternoon, one and all. Hello. 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 My voice is audible, madam.
You are audible, sir.
Okay, madam.
You are perfectly audible, sir. Please continue.
Okay, madam. So first of all, I would like to express my sincere thanks to MHRD and the organizers of this FDP. The principal of Jabalpur Indian College, Dr. A.K. Sharma, and the coordinators, Dr. Bhavna Singh and Dr. Durgesh, Nandini, and Dr. Mamta, and today's distinguished and excellent professor, eminent professor, Professor Ravindra Pandey Garu, and the participants also. So, because by using because of this FDP, we have learned so many things, new concepts. So my heartfelt thanks to Professor Ravindra Pandey Garu for his excellent and delivered lectures throughout this session. And one more thing, because we have learned so many new topics, because that is density function theory and photovoltaics and solar cells and ESSC and supercapacitors, etc. Of course, I did my research work in experimental, but I don't know about the new remaining topics about, that is DFT and some other topics also. So on this occasion, I request Professor Pandey Garu, please give me your guidance to my future academics also. And definitely, I believe that all the participants definitely they will get this course is very helpful to all the participants. And definitely, I congratulate. Definitely, this course will helpful to all the participants, and also I congratulate all the team, that means organizers and course coordinators by conducting this course in a smooth manner. In future also, please conduct some more courses. Okay, just like that. Okay, thank you very much, sir. Thank you.
Thank you. And like I said, please reach out to me. Even if I cannot help you directly, I'll provide indirect helps through the contacts and so on. Thanks again.
Yes, sir. Yes, sir. Thank you, sir.
Thank you, Somesh, sir. Is anybody else?
Yes, ma'am. Dr. Hinge here.
Dr. Hinge.
Oh, hi, Dr. Hinge.
Sir, good afternoon, everybody. So first of all, I must congratulate the coordinators of this GIAN program, Dr. Bhavna Singh, Dr. Durgesh Nandini, and Dr. Mamta Lambert, for organizing such a beautiful and fruitful workshop. Sir, I must thank to you, Pandey sir especially, to conduct the lectures properly, and sir, you explain each and everything in a simple manner and we understand properly. Sir,
Dr. Hinge, just to always remember, is if you come from a small town, we had to really explain nicely. You know, I come from Sagar.
Yes, sir.
It provides the basis, but please go ahead.
Yes, sir. And sir, सबसे अच्छी चीज जो लगी इस प्रोग्राम की मुझे वो ये थी कि सर पूरा वर्कशॉप आपने उसको किया. So you start from the basics and you end to the final future of the nanotechnology. So it will be very fruitful for me, sir. Thank you very much, sir.
But let me add you two things. Is the structure of the workshop, I really give credit to Dr. Singh and Dr. Nandini. But the timing part is really goes to our coordinator, Dr. Mamta Lambert. Because even if I'm 30 seconds late, she said, sir, please do it, you know.
Sir.
So it helps to have a good team.
Really, sir, this is the most beautiful part of this workshop, that you start by 10:30.
Just because of Professor Lambert.
Yeah. Thank you, madam. Thank you very much.
लेके वो खड़ी हुई थी.
Thank you, sir.
Good. Thank you.
Thank you, Professor Hinge. Anybody else?
Yes, ma'am. Bhakti here.
Go ahead.
Yes, Miss Bhakti.
Firstly, good afternoon, everyone. I would like to thank JC Jabalpur and all the coordinators who organized these amazing sessions, and it definitely provided an extra edge to our learning. And thanks to you, sir, as you gave wonderful deliberations from beginner to expert level. And also I want to add that I found the topic synthesis, carbon nanotubes very much related to the field of research and chemical engineering. And for me, so everything was very much related and understandable. Thank you once again.
So Bhakti, I think is, since you are still a student, you have, if you would like to pursue, I could see the role of chemical engineering, you know, the background.
Yes, sir.
Moving from lab to, I call the real world, you know, because we can always do all these things, this material is so good, this and that, but someone has to fabricate those materials. And that's, I believe,
Yes,
chemical engineers definitely going to play a larger role because we have the knowledge of chemistry. So please follow on your dreams. You know?
Yes, sir. Definitely. Thank you, sir.
Thank you, Ms. Bhakti. Is anybody else from the participant who want to share their feedback?
Sir, hello.
Yes, please continue, Dr. Nelsa.
Hello, I am Dr. Nelsa from Kerala. Actually, the course was very nice, and he gave the lectures very nicely. And actually, I am from electronics background, and I got actually a fundamental from chemistry background.
We lost you, Dr. Abraham.
Using this of planning to, that's, definitely I think this will help. Thank you, Pandey sir, for the great lectures you gave us, and we are hoping for your help in the future also. Thank you. And also once again, I thank you all the coordinators. I thank all the coordinators for coordinating such a nice course. Okay, sir. Thank you once again.
We'll do it. Yeah. Thanks.
Ma'am, am I audible?
Yes.
Okay. Good
Yes,
afternoon,
Arishi, please
everyone.
continue.
Okay, so I also like to share my feedback. And this was a very nice session. Thanks a lot, sir. And thanks a lot to JC team. Ma'am, thank you so much for organizing such sessions for us. And like the first 3 days were like the recap of my MSc degree. And that was my main expectation, as I have told earlier. And after that, when we moved into the deeper topics about the, tutorial sessions and software related things, I got a little slow in understanding those topics, but still I used to rewatch the lectures in the night from YouTube. So thanks a lot, Mamta ma'am, for that. Like you have shared those things in YouTube, and thanks a lot again. And I'm looking forward for such similar sessions, ma'am. So please organize such sessions again in JC, ma'am. Thank you so much, and thanks so much, sir. Thank you.
Is anybody else? Okay. Thank you so much, everyone, for sharing your thoughts. And now I would like to invite Dr. Mamta Lambert, our Institute Local Coordinator for GIAN Course Program. Thank you, ma'am. Over to you.
Good afternoon, all dignitaries connected with us in virtual mode, respected expert and foreign faculty, Dr. Ravindra Pandeji, respected principal Dr. A.K. Sharma, former principal and former local coordinator Dr. S.S. Thakur, my dear colleagues and my dear participants. I feel honored and privileged to get an opportunity being a local coordinator to propose the vote of thanks at the end of the third GIAN course. I, Mamta Lambert, on behalf of Jabalpur Engineering College and entire team of GIAN at institute level, I firstly thank MHRD to launch GIAN on 30th November 2015 at IIT Gandhinagar and simultaneously launched at IIT Kharagpur. I am very much thankful to the National Coordinator GIAN and Implementation Committee for their kind support and guidance throughout the GIAN course management and implementation. They provided us the funds before starting the course. Without it could not be possible the live streaming because many gadgets were needed for smooth conduction in the live streaming. I acknowledge the initiative made by IIT Kharagpur to lead National GIAN program to bring international faculty Dr. Ravindra Pandey in virtual mode. The major success of the entire GIAN program goes to our foreign faculty, Dr. Ravindra Pandey. I express my earnest gratitude for the painstaking efforts that Sir has taken for ensuring successful conduction in a well-mannered way of virtual program. I also thanks to the principal for providing encouragement, kind support and environment for conducting the course in online mode. I also thanks to the former principal and former local coordinator Dr. S.S. Thakur for making efforts in this direction to ensure that Jabalpur Engineering College becomes the host institution for conducting third International GIAN course. I convey thanks to all participants who have connected virtually from all over India. A special thanks to Master Rajneesh, Miss Arya, Master Samuel, Master Isaac and Mr. Rajiv for their full technical support in the live streaming and recording and managing all the streaming in an attractive manner. They made a setup before a day of starting this program. Whatever I was planning to implement, they all made it possible. I thank to all my team members, Professor Amit Baghel, Professor Jyoti Bajpai for their coordination. I thank to Professor Loveleen Kaur, Head of the Department ID, for providing us the environment. From there it could be possible to conduct the program in a virtual mode. I thank to our supporting staff, Mr. Moolchand Patel, Mr. Prem Narayan, Mr. Ramu Soni, Mr. Richard, Mr. Ram Prasad, Mr. Amit Ojha for their continuous support. I thank whosoever directly or indirectly connected in organizing this course. I thank to course coordinators Dr. Bhavna Singh and Dr. Durgesh Nandini for taking the necessary steps in a short period of time for making this course a successful event. We all are missing Dr. Ruchi Nigam. She was associated with this project, but we lost her in COVID-19 pandemic. I thank Lord Almighty for keeping all of us safe in COVID-19 pandemic so it could be possible to organize this course after rescheduling. It is a proud moment of our institute to conduct third GIAN course in the Platinum Jubilee year. Our institute is celebrating this year as Amrit Mahotsav. All the lectures and tutorials are available on YouTube channel by name Mamta Lambert. You can go to my channel and download the lectures in the future and you can be benefited from these lectures. Thank you so much. I have tried my level best. Thank you.
I think what do I say is really fun and like a lot of you said is the basics, and sometimes as a teacher you forget about the basics. And I really like to give tutorials because giving a professional talk is very, very easy. And from day one I realized that once we have either engineers or physicist, chemist or mathematician, so it took some time to lay in the talk. But thanks again for participation, organizers. I've really given them a lot of thanks, the host. And so hope to see you somewhere, sometime in near future. Thank you again. Namaskar.
Thank you also for your kindness. It has been honor to have you with us. call Dr. Durgesh Nandini, our course co-coordinator for GIAN, and give a photo. Over to you, ma'am.
Good afternoon, everyone. Thank you, Bhavna Singh, for giving me this opportunity. I feel privileged to express my deep gratitude to our eminent speaker, foreign expert, Dr. Ravindra Pandey. Michigan Technological University, Cotton, Canada, is USA. His excellent guidance, presentation, and providing useful information which is related to today's and future aspects and making this program interesting, meaningful, and very much truthful. Respected Dr. Mamta Lambert, local GIAN course coordinator, Rajiv Lambert, Dr. Bhavna, and Professor Amit Baghel sir, and dear participants who are connected with us. It is not a mere gift wrap thanks, but I am really expressing my heartfelt gratitude with you all. It has been amazing to connect with everyone. It is my great pleasure to propose the vote of thanks to all who have constantly helped us in making this international 5-day course on nanomaterials and design for every energy application such a resounding success. First, I would like to thank our mentor, coordinator GIAN IIT Kharagpur for providing this great opportunity to us. I would like to thank our principal, Dr. A.K. Sharma, for permitting our department to conduct this program. I would also like to extend my thanks to our former principal, Dr. S.S. Thakur, for his valuable support as the proposal was sanctioned during his tenure. Our beloved Dr. Mamta Lambert, local coordinator of this course, deserves a huge word of thanks for her continuous guidance, support, and valuable efforts. I am also thankful to all participants for their precious presence. As we know that no program can become successful with a single person. So I extend my big thanks to our entire organizing team, Dr. Mamta Lambert, Dr. Bhavna Singh, Professor Amit Baghel, supporting staff Amit Ojha, Patel, Ram Prasad, and volunteer Rajnish Kushwaha, Arya Singh Thakur, Master Isaac, Samuel Lambert, and participants of the program. At the end, I would like to thank all media persons for their support. Once again, thanks to all. Thank you.
Thank you very much, ma'am. It is my request to all the participants, please do not forget to share the feedback link available on your Google account.
Again, I would like to request all the participants, please fill feedback form as well as submit the MCQ available on your Google mail account for obtaining the certificates. Thank you.